So in dealing with any kinematics problem involving acceleration, we first recognize that we have four equations to work with. Each of these equations, if we go through, we can look at the kinematic variables that are present. We have final positions represented, we have initial positions represented, initial velocities, times, and accelerations. So in that first equation alone, we have 5 kinematic variables represented. If we go to the next one, we see that we have the positions, both velocities, and time. The first equation didn't include final velocity. The second equation does. So there's our 6th kinematic variable. The third equation deals with velocities, accelerations, and positions. And the last just involves 2 velocities and acceleration and time. So there are 6 kinematic variables. If we look at this problem, how high does a coin go if it's flipped with an initial velocity of 5 meters per second? We need to list what we know about the problem in terms of those 6 kinematic variables. I call this writing out your inventory of variables. So we know that the object is moving upwards at 5 meters per second to start. So its initial velocity is positive 5 meters per second. We also know that its highest point occurs when the coin is momentarily at rest. And so therefore, its final velocity, which ends the problem ends when the coin gets to that high point, final velocity is 0 meters per second. The question of where is it to begin with is completely arbitrary. I'm going to go ahead and say the coin starts at a position of 0 meters. And where it ends, well, the problem ends at its maximum height, which is unknown. How long does it take to get up there? That's also unknown. The acceleration on its way up, recall that gravity doesn't really care whether you're moving up, down, or you're stationary momentarily. It's going to pull you down, and I'm going to use 10 meters per second squared here. Depending on the problem, you may want to use 9.8. Now, this is very important. It's negative 10 meters per second squared. Remember that I called the initial velocity upwards a positive velocity. Acceleration is pulling consistently at 10 meters per second squared downward, so we must indicate that with a negative. If I indicate that with the positive, the math will tell me that the coin actually gets faster and faster and faster as it goes up, which we know isn't true. So the next step is to look at our unknowns. Our unknowns at this point are final position and time. The question asks us how high does it go? In other words, it's asking us what is its final position. So therefore, I'm looking for y final, and I'm not interested in time. The variable that I'm looking for must show up in the equation that I use. In this case, the equations I wrote in terms of positions being x's, we're using y's here. They're really the same thing. So my options thus far are the first equation, the second equation, and the third equation. The fourth equation does not include positions, so I can't use it. The top 3 all include final position. The problem is, if I have final position in the equation, that's not enough. I also cannot afford to have time. Otherwise, I have 2 unknowns in one equation. So therefore, this first equation and the second equation both have time represented, and so I can't use those. So equation number 3 is my equation. So because I'm looking for a final position, I'm going to go ahead and solve for final position before I throw in any numbers. This is often a useful tool, solving algebraically, because you can see what all the possible circumstances are surrounding the problem. I can look at what happens if I increase a, or I decrease initial velocity, or something like that. So I'm going to solve for y final, and I get v final squared minus v initial squared divided by 2a plus y initial equals y final. So for instance, if I increase y initial, I know the whole left side will have to increase, y final will have to increase. If I increase v initial, the numerator in this will become much larger, in this term will become much larger, dividing by the same term, so this whole fraction becomes much larger, which means my final position would become much larger. So it works out. All right, so now I can plug in variables. I know it started at a position of 0 meters. It's going 0 meters per second squared when it finishes. It started out going 5 meters per second upward, and the acceleration is negative 10. I evaluate that. This is negative 5 squared, which is negative 25 over negative 20, which is positive 1.25 meters. Now that number doesn't really mean anything until I refer back to the scale and the axes that I set up in my problem. I started the object at a position of 0. It finishes, when it's 0 meters per second, it finishes at 1.25 meters, which is 1.25 meters above the hand, and there's my answer. That's how high it goes above the hand. I could have decided that the final position is a position of 0 and solved for the initial position. The answer that I would have gotten was negative 5 or negative 1.25 meters, which would have given me essentially the same answer, but I needed to interpret it. This process can work for any object, whether it's freely falling or not freely falling. Any object that is accelerating can be analyzed in this way, using the kinematic variable inventory, looking at what equation you need to use, and solving for the appropriate variable. The only difference between freely falling bodies and other accelerating objects is when an object is in free fall, the acceleration must be negative 10 or negative 9.8. It's the acceleration due to gravity. In all other problems, the acceleration depends on what the problem is and what you're told. So that's how you work with objects which are accelerating.